Okay, so let's start now with thermodynamic potentials. And what I'm going to do at first is to write the fundamental thermodynamic relationship. So remember, differential of U, I can break it down in any way I like. And I decide to break it down in reversible heat as usual and reversible work. From Clausius' theorem, we know that reversible heat is TdS and the reversible infinitesimal work is PdV. Thinking always, of course, of an expansive system, single component, okay? So, fine. So if you just take a look at this expression and think about it for a while, you realize that it looks as if we have expressed the property of state, internal energy, as a function of two independent variables, which are in this case S and V. And then it seems that we took, just by applying the chain rule, the differential of this, so the partial with respect to S at constant volume plus the partial with respect to volume at constant S. And just identifying terms here, we see this thing must be equal to that, and this thing must be equal to that, well, actually with a minus sign. So, in other words, the partial derivative of internal energy with respect to S at constant V is T, and the partial derivative of U with respect to V at constant S is minus the pressure. Okay, so fine, so let's just put some names to these things. So I'm going to call entropy and volume, I'm going to call them the natural variables of the internal energy, okay, and the partial derivative of, well, let's just write it off, internal energy, and the partial derivatives of the internal energy with respect to its natural variables give you the conjugate variables. So these ones are conjugate variables of the internal energy. So temperature is conjugate to entropy, and minus pressure is conjugate to volume. Okay, that's just terminology. But whenever you have such identification, you can arrive to a non-trivial relationship between conjugate variables and partial derivatives, actually, of conjugate variables of your system, just by applying Schwarz's theorem, because you know that internal energy has continuous second derivatives, which means that the partial derivative of with respect to volume of the partial of U with respect to S at constant volume, which is what I have here, equals the other derivative, which is the other cross derivative, which is the partial derivative of U with respect to V at constant S. Okay, so if you just replace what these terms here are, you arrive to the really nice expression, partial derivative of T with respect to V at constant entropy, which is a very weird type of derivative, is equal to minus the partial derivative of P with respect to S at constant volume. Okay, so this is the first of a series of relationships that we are going to be using a lot in this chapter and also in the coming chapters, which is called Maxwell's relation. So this is the first Maxwell relation. Okay. A couple of remarks before I move on, so that well, you know, maybe you have some of these questions already in the back of your mind. So first of all, so far when we have solved some practical example, we have always chosen as independent variables for the single component expansive system two variables out of the set PVT. Okay, and okay, that makes sense. When you know you only need two variables, that was something that we had established in the very beginning of the course, but which variables you choose it's your thing, right? So you are free to choose anything you like. And actually, in the very beginning of the course, we only knew pressure, volume, and temperature, but now we know more. We know U and we know S. Okay, so we could, in particular, choose any two out of this set. And actually, we're going to keep defining more of these quantities. So we can choose to describe a single component expansive system as independent variables. We can choose anything we like. For instance, we can choose indeed entropy and volume. Okay, so that's the first thing that perhaps some of you were thinking about. The second thing I wanted to remark is that okay, we have already solved some problems in which we have written u as a function of something, for instance temperatures and volume. This is something we did when we derived the first energy equation just at the very end of the entropy lecture. And when you do that, you can still calculate du as the partial derivative of u with respect to t, constant v dt, and the partial of u with respect to volume at constant temperature dv, right? So what is so special about entropy and volume? Why are not the natural variables of energy the temperature and the volume? Okay, so what's special about entropy and volume, that specific combination? Well, if you remember what we got when we calculated the first energy equation, just copying, scrolling up in the lecture notes, that's partial derivative of u with respect to v at constant t is a complicated expression. It's not a super complicated expression, but it is definitely not as neat as what you get when you choose properly the natural variables. Okay, so we know that the partial derivative of u with respect to v at constant t involves some further derivatives, a combination of variables. But when you take the partial derivative of u with respect to with respect to v at constant s, you get minus the pressure, just like that. Okay, so the only thing that makes natural variables special is that the corresponding conjugate variables are simple. Okay, and you want simple things because you want to work with them afterwards. Okay, so that's the only reason why you can get these neat, nice relationships, these Maxwell relationships. Okay, it's nothing wrong about expressing energy in terms of different variables which are not its natural ones. Maybe that's what you need for the problem you need to solve. In particular, remember that all we wanted to do in the end of the entropy chapter was to evaluate this derivative. So the most rational choice of variables is volume and temperature, indeed, as independent variables, to write out the internal energy. Okay, so in that case, we didn't have any choice. So, okay, these were the two remarks that perhaps were bothering you a little bit. And now I will show you how to obtain another of these Maxwell relations. So, to do that, I have to define a new quantity. Okay, so this is going to be called the free energy, or Helmholtz free energy. And this is another property of state, or another function of state. So how do you define it? Well, F, and this is so far a definition. Later on in this same lecture, I'm going to give you physical intuition of why would you care about such a quantity and what is its physical significance. But for now, I want just to define it. And okay, so what is this? Imagine you have any equilibrium state of your system. You calculate its internal energy. On the other hand, you calculate the entropy of that state. You have a look at what's the temperature of that system in that equilibrium state. And you combine all of these things into this function of state. Okay, so for each equilibrium state of the system, f adopts, in principle, a different value. Okay, so it's a function of state and not a process variable. Okay. So let's just take the differential of f, defined like that. Just applying the rules of differentiation. This is minus t ds and minus s dt, because it's the differential of a product. And we know what the differential of u is because we know the fundamental thermodynamic relationship. So this is TdS for reversible heat minus PdV for infinitesimal reversible work. And this is minus TdS, which we carry from above, minus SDT. And just notice that this goes with that. Okay, so in the end, I'm left with minus PdV minus SDT. Okay, so what we see, once again, is that this quantity, the free energy, or the Helmholtz free energy, or it's also called the Helmholtz potential, has natural variables V and T. And the corresponding conjugate variables, the partial derivative of f, with respect to v at constant temperature, is minus the pressure. So you see, it's a very neat relationship. It's not complicated at all. And the partial derivative of again, with respect to t at constant v, is minus the entropy. Okay, So now that we know this, we can do the exact same thing that we did with the internal energy. And we can apply Schwarz's theorem to say that, let me see if I get it right, the partial derivative of f of s with respect to v at constant t is equal to the partial derivative of p with respect to t at constant volume. Okay, we derive this with respect to temperature, and we derive this with respect to volume. And we get, again, another highly non-trivial relationship involving derivatives of entropy, volume, pressure, and temperature, which is going to be tremendously useful later. This is called, just for historical reason, third Maxwell relation. We don't care if it's the third or the fifth, therefore only, but we have to remember what the relationship is, right? And next, I'm going to show you how to systematically obtain more of these things and how to systematically define new properties of state from the ones we know, from energy and entropy.